So, we're going to talk about Newton's law of universal gravitation. It says that all objects attract to each other with a force of gravitational attraction. Gravity is universal. This force of gravitational attraction is directly dependent upon the masses of both objects and inversely proportional to the square of the distance that separates their centers. So, this law says that there are two forces that are interacting each other. Obviously, each of these forces, they have a mass actually. So we're going to imagine this and try to draw it as MA and MB. As they say that they are interacting, we're going to draw a line that we're going to call the action force line. And then we know that the force is inversely proportional to the product between both masses. So in this case, the force is inversely proportional to mass A per mass B. And it also says that the distance between the both objects is pretty important because the force is inversely proportional to the reverse of that distance squared. We can read the magnitude of this vector force as the gravitational constant that we're going to see later on times the mass A times mass B over the distance between both masses squared. Now we're going to draw this in our Cartesian plane that is going to be separated by the y-axis, by the z-axis, and the x-axis. We are going to draw our vector r, which is the distance between the two masses that are interacting to each other, and we're going to draw an angle. This angle, we're going to name it delta. Then we're going to draw another angle, and we're going to name this phi. We are doing this because we want to represent this in a circular way. So at first we had x, y, z to express coordinates, but now that is exactly the same as saying r, delta, phi. It's another way to write this. So if we want to write the magnitude of this vector of force, this force vector, we are going to write that as f of r with its unitary vector, in this case it's r unitary, plus f of delta times its unitary vector plus f of phi times its unitary vector, and this is exactly the same as if we wrote f of x times its unitary vector plus f of y plus f of z, and both of them by its unitary vectors. In this case, we're going just to focus into the f of r times its unitary vector because we just want to know. It is important to mention that we're trying to get the interaction between them. So our vector from mass B, it's going to be from the opposite side, and in this case its unitary vector, it's going to be negative. So if we write again the formula of the magnitude of this, it's going to be the vector of force, it's going to be equal to the gravitational constant plus the mass of A times mass of B over the distance between them squared times its unitary vector, that in this case is going to be negative r unitary. An interesting fact about this is that if we plug this formula into Newton's second law, we can get a lot of things, like for example the imaginary orbitals of the planets in the space, and for example, where do we want to place one telescope in space, or maybe one satellite, and that kind of stuff. This is why it's very important, this law. So all scientists and people that works in NASA and all kind of nerds are pretty thankful because Newton realized about this formula, because that's why we can learn more in the actual days. Well, now we're going to see again from another point of view the interaction between both masses. So we know that mass B has an interaction force, and we're going to write it as F of B when interacting to A. So it's going to be like a F vector, that is force vector actually, and lowercase we're going to write B A, because it's the interaction of B and A, not from A to B, from B to A. And then we're going to write our formula, and here it's something very important because here we are going to know the real value of the gravitational constant that is given by 6.673 times 10 to the minus 11 newtons per mass squared over kilograms squared. And it has an error, I don't know if it's important to mention, I guess yes, that has an error of 0.0014%, which is a pretty huge error. And if you are trying to guessing, hey, is this force pretty pretty strong? No, it isn't. Actually, it's one of the weakest forces around the world, or well, not around the world, around the universe. That will be the correct term. We can conclude something here, that the force that is experimenting, the force of A to B, is going to be the same as the one that is exerted by the minus the force of B exerting to A. So it's related with Newton's third law, that it's action-reaction. Well, now this is a time when I try to guess uh, where can I apply this kind of knowledge in real life. Well, it is something that got me thinking a lot of time, because uh, my girlfriend told me that she was pretty attracted to me when she first saw me, and I said, "Oh wow, she's so cute," and all that kind of stuff. But when I read this, I realized that that was impossible. Or maybe she could be attracted to me. Yeah, she actually, it's from physics. Obviously, we had an attraction to another person, that's obvious, but it's a pretty low attraction. So that attraction, it's not an important number. So if she told me that, I think that she was lying to me, or her hormones were up and down. I don't know. Maybe it's because she just wanted to say that, hey, I love you. Okay. Well, anyway, so I'm going to prove you that she is wrong. So as I said before, I'm going to prove that she's wrong. Okay, so try to imagine that the first time we met, we were 15 meters apart from each other, and well, my mass is 70 kilograms and her mass is 48 kilograms. So then, with this data, we're going to plug this data into the formula and to know what was our attraction. Well, after making all the calculations, we can conclude that the attraction force between us was about 1.5 per 10 to the minus 9 newtons, which is pretty low. So she was lying to me. Don't worry, babe, I love you. So, guys, girls, if your boyfriend or girlfriend told you, hey, I was attracted to you by the first time I saw you, he or she is lying to you.